Right, we'll wait a few minutes and then we'll start. Okay, I'll now share my screen. Okay, I'll start the lecture now. If anyone wants to join, please admit them. Right. So today is the fourth live session of the course Structural Biology, and we will learn more about X-ray crystallography. So first, we will talk about how the X-rays are produced. So this is a cathode ray tube, and what happens is that at one end of it, a voltage is supplied. So this is connected to an electric source, and an electric current passes through this wire, keeping this at a high voltage. So what happens due to the passage of this electric current, this filament heats up. And when it heats up, electrons are emitted. which is called thermionic emission. Now, when electrons are emitted from this wire, there is an anode here which is maintained at a positive charge. So since the electrons are negative charge, they are attracted by the positively charged anode and they accelerate towards the anode at a high potential difference of 50 to 100 kilovolts. Now this anode is usually made of tungsten or copper, and it is made positive with respect to this wire or filament. And so it attracts the negatively charged electrons, causing an acceleration. The accelerating electrons collide with the anode and they lose this acceleration, and so they lose the kinetic energy. The kinetic energy of the electrons are then released in the form of X-rays. So that is the concept of the formation of X-rays. Now, while traveling from cathode to anode, the electron is not scattered. It is focused by something called a focusing cup. This is to maintain a focused beam of electrons so that the X-rays are also not scattered everywhere and are focused. The distance between this filament and this anode is generally around 1 centimeter, and this positively charged anode causes so much acceleration in the electrons that its velocity is raised from 0 to almost half the speed of light. So there is a huge acceleration, and that huge kinetic energy is lost in the form of X-rays. Again, if you see here, the projectile electron, which was released by the filament, interacts with the orbital electron of the target atom. So it strikes the atoms of this anode, and this electron kinetic energy is converted. Some of it is converted into X-rays, only around 1%. And the rest is released as heat or in the form of IR radiation. So the huge amount of kinetic energy that the electron gains while accelerating, only 1% of that is converted into X-rays. Now, if we look at the electromagnetic spectrum, we can see there are different kinds of electromagnetic waves, starting from radio waves, which have the highest wavelength, and then microwaves, infrared or IR, visible wavelength, ultraviolet, X-ray, and gamma rays. So right now our topic of focus is the X-rays, and you can see that the wavelength of X-rays is in the range of that of atoms and macromolecules, which is why X-rays can be used to find out the atomic structure of macromolecules. As you can see here, the wavelengths that are typical for X-ray crystallographic applications range from 0.05 nanometer to 0.25 nanometer, or you can say 0.5 to 2.5 angstrom. So this is the range of X-rays that we are interested in. Next, we will talk about continuous and characteristic X-rays. So continuous X-rays are also called Bremsstrahlung radiation, which means breaking radiation. What happens here is the electron which is accelerated from the filament reaches the atom, and it releases a radiation across many different wavelengths. So if you look at this energy or wavelength, you can call it, the Bremsstrahlung radiation is a range of energy. So it is not a particular wavelength, it is a range of wavelength that is released. And so since so many different wavelengths are released, it is called a white radiation, because as you know, white light consists of 7 colors or 7 wavelengths. So since this breaking radiation consists of a continuous range of wavelengths or energies, it is called white radiation. The more important kind of X-rays that we will be focusing on is the characteristic X-rays. So what happens here is that this is your electron which is accelerated from the filament. It collides with the anode. This is an atom of the anode. So when it collides with an electron of the anode, this electron is deflected outwards. But what it does is that it pushes one of the inner electrons of the atom of the anode outside. So now in the anode atom, there is a vacancy over here. This is an unstable state, and this vacancy quickly needs to be filled by an electron from one of the outer shells. So you know that between different electronic shells, the energy is a constant. So when an electron from, say, the L shell fills up the K shell, the energy difference between L and K shell is released as an X-ray. So this is called a characteristic X-ray because it has a certain wavelength, meaning it has a certain energy, and that is the energy difference between the L shell and the K shell. Again, if an electron from the M shell goes to fill the vacancy of the K shell, then also the energy difference between M and K shells is released as a characteristic X-ray. So here in this diagram, if you see, there are two characteristic X-rays have been shown. K alpha, which is basically an electron from the L shell fills up the vacancy in the K shell, and K beta, which is when an electron from the M shell fills up the vacancy in the K shell. So as you can see, these have a single wavelength, and so they are called characteristic X-rays. Next, we will learn about the properties of these characteristic X-ray. So not every electron in each of the shells has the same energy. So the shell that is closest to the nucleus is called the K shell. The shell after that is L, and the one after that is M. But this does not mean that all the electrons in the M shell have the same energy. Even the M shell is subdivided into different shells, and the same for the L shell. So suppose your accelerating electron knocks out an electron from, say, this electron from the K shell. So this vacancy can be filled by either of the two subshells of the L shell. So you can have two different kinds of radiations. Here it's shown as K alpha 1, K alpha 2. So if you look at this division shown here, so this is the energy level of the K shell. These are the sub-energy levels of the L shell. So if you come from L to K, you can have different K alpha 1, K alpha 2 radiations. Similarly, if you come from M shell to K shell, you can have K beta 1, K beta 2 radiations. So like this, even within a shell, you can have different subshells of different energies. So different metals will provide different wavelength. So why is this? This is because the energy levels depend on which atom the energy levels belong to. So for different metals, the energy levels, and so the difference between the energy levels is different. So according to what wavelength you want, you simply have to change the composition of the anode. So we must have a source of monochromatic X-rays for X-ray diffraction. Monochromatic basically means you want X-rays of a particular wavelength. So what you want is characteristic X-rays. We must try to eliminate white radiation and K beta radiation to use only K alpha. So white radiation is not of much use because, as you saw in the previous slide, it is made up of many different wavelengths, but you want only one specific wavelength. And generally K beta is also eliminated, and K alpha is the most important wavelength or of the characteristic X-ray that is used in X-ray crystallographic studies. We will now talk about Bragg's law of X-ray diffraction. So what is shown here are the lattice points of a crystal. And this is an incident beam of X-ray. So suppose you have taken two X-rays that are parallel to each other. So this X-ray comes, it reflects off this atom. Here it is called diffraction, and this is the diffracted ray. Now the ray 2, which is parallel to ray 1, is traveling an extra distance compared to ray 1. So if you draw perpendiculars AC and AD, you can see that ray 2 travels this distance extra compared to ray 1. So if you want to find out what is this distance, we will call the distance between the two crystal planes as d. So this is d sine theta and d sine theta. So 2d sine theta, here you can see d sine theta plus d sine theta is 2d sine theta, is the net distance that is traveled extra by ray 2. D is the distance between these two crystal planes, and theta is the incident angle that the incident beam is making with this crystal plane. So this ray 2 is traveling a total extra distance of 2d sine theta. Now, if this 2d sine theta is an integral multiple of the wavelength, then this diffracted ray 1 and diffracted ray 2 will have constructive interference. So what is constructive interference? Here you have two waves, X and Y. If the peak of the wave and the trough of the wave are in the same place, then they will interfere constructively, meaning that the amplitude will become double. So here the peak is also doubled and the trough is also doubled. Similarly, this is called constructive interference. So another case is when you have the peak of one wave and the trough of another wave. So these two will cancel each other out, and this is called destructive interference. So in order for the diffracted ray 1 and the diffracted ray 2 to interact constructively, they have to be separated by a distance which is an integral multiple of the wavelength. So the 2d sine theta must be an integral multiple of the wavelength of the ray, where this n is an integer value like 1, 2, 3, 4. So only when the two rays, ray 1 and ray 2, after diffraction are separated by a distance of which is an integral multiple of lambda, can they combine constructively like this to give larger amplitudes. And you need larger amplitudes because you know that the intensity is the amplitude squared. So you want constructive interference so that you get a high intensity diffraction pattern. And for constructive interference, you need this criteria to be true. That is, 2d sine theta is n lambda, where d is the distance between the crystal planes, theta is the angle that the incident beam makes with the crystal plane, n is an integer 1, 2, 3, 4, and it is also called the order of reflection. So if n is 1, you say it is a first order reflection. And theta is also known as Bragg angle. So a few things to remember about the geometry of this Bragg's law is that the incident beam, the normal to the reflection plane shown by this dotted line, and the diffracted beam are always coplanar. So here they are in the plane of this slide. The angle between the diffracted beam and the transmitted beam is always 2 theta. So transmitted beam is basically if this incident beam passed through without any deviation. So you can see this is theta and this angle is also theta. So the transmitted beam would be like this. It would be at an angle of 2 theta to the diffracted beam. Now, you know that sine theta cannot be more than unity. So the maximum value of this is 1. Generally, it will be less than 1. And so n lambda will be less than 2d. And if n is 1, lambda is less than 2d. So we should choose the wavelength of the characteristic X-ray in such a way that the wavelength is twice that of the distance between the crystal planes. So suppose we want to study a crystal. So what wavelength of X-ray should be used to study that crystal? That wavelength should be decided first by measuring the distance between the crystal planes and taking a wavelength that is less than twice that distance. Only then will we get a intense diffraction pattern through the constructive interference. Next, we will talk about periodicity and symmetry in a crystal. So why do we need to know the symmetry of the crystal? Firstly, if you know the symmetry of the crystal, we can just study a unit cell. So instead of studying the whole crystal, if you identify that region of the crystal that is repeating called the unit cell, you can just study that. So it reduces the data collection by reducing the number of unique reflections to collect. So you can simply take reflections from the unit cell and you can extrapolate that to the entire crystal. So it reduces the data collection time as well as effort. And symmetry may also be useful for phase determination. So these are the reasons you need to know the symmetry of the crystal. Now, a crystal has long range ordering of building blocks that are arranged in a conceptual 3D lattice. So basically, an asymmetric unit is the smallest portion of a crystal to which symmetry operations can be applied to generate the complete crystal. So this is an asymmetric unit. If you have, suppose, we will talk about the symmetry operations later, but for now, assume that this black portion that is shown here, this is a center of inversion. So basically, any point on this blue arrow, if reflected, should appear on this purple arrow. So for every point on this arrow, you should have a point on the purple arrow opposite to it. So from an asymmetric unit, after carrying out a symmetry operation, which is basically here the center of inversion, which we will learn more about later, you can get the unit cell. The unit cell is a building block of minimum volume, which is repeating to get the entire crystal. So from the unit cell, by repeating in all three dimensions, X, Y, and Z, you can get the entire crystal. Next, we will talk about space lattice. An array of points in space such that every point has identical surroundings is called a space lattice. So whichever point in the space lattice you choose should look identical to you. So here only a portion of the lattice is shown, but actually this extends to infinity in all directions. So if you choose any point in this, they are surrounded by the same number of neighboring points at the same distances. So this implies two properties. One is that lattices have translational periodicity, meaning this is one cube. You can have another cube just beside it, another just below it. So you can translate the cube to form the entire lattice. So in Euclidean space, lattices are an infinite array. Like I said, this is just a small portion of the lattice. You can actually extend them to infinity in X, Y, and Z directions to get an ideal space lattice. And this is a unit cell of the lattice, which is the smallest repeating unit. So in space lattice, you can have 1D, 2D, or 3D lattices. We will first talk about 1D lattices, which is basically the repeating unit is a single point. And this single point can be repeated infinitely in both plus x as well as minus x directions. So 1D lattice is formed by infinitely repeating a point in a single axis, both the positive and negative directions. This lattice can be defined by a single lattice parameter A, which is the distance between two lattice points. So knowing A is enough to define the whole lattice. In 1D, the action of a mirror operator is the same as that of a twofold or inversion operator. So imagine you have a mirror between 2 points. So the distance from the mirror to either of the point is A by 2. Because the total distance is A and you have a mirror between them, then A by 2 is the distance of each point from the mirror. If you go to the next point, the distance is A plus half A, so 3A by 2. And similarly, you can get an infinite lattice simply by reflecting on either side of the mirror. In this case, you can also consider, instead of a mirror, that it is a rotational axis. So if you have a rotational axis passing between 2 points and you carry out a 180-degree rotation through that axis, then these 2 points will be interchanged. So that is called a rotational symmetry. In this case, which is the case of the 1D lattice, the mirror and the rotational axis are at the same place. The unit cell for a 1D lattice is a line segment of length A. So basically the unit cell consists of a single point which is at a distance A from the next point. Next, we will talk about 2D lattices. So two basis vectors generate the lattice. There are 3 lattice parameters which describe a 2D lattice. The distance between 2 points along the x-axis called A, the distance between 2 points along the y-axis known as B, and the angle between A and B known as alpha. So these are the 3 parameters that you need to completely define a 2D lattice. 4 unit cell shapes in 2D lattices can be used. One is a square where A and B are equal and alpha is 90 degree. The second is a rectangle where A and B are not equal and alpha is 90 degree. The third is called a 120-degree rhombus, where A and B are equal and alpha is 120 degree. So if you look at A and B from this direction, this is A, this is B, and this angle is 120 degree, that automatically makes this angle 60 degrees. And the fourth is a parallelogram where A, B, and alpha are all independent of each other. So that is the most general type called a parallelogram. The final kind is the 3D lattice. So 3D lattice can be defined with 3 basis vectors. This is a generalized 3D lattice, and this is the unit cell or the repeating unit of that lattice. And it is defined by 6 lattice parameters. 3 distances, A, B, and C along X, Y, and Z axis, and 3 angles, alpha between B and C, beta between A and C, and gamma between A and B. So if you know A, B, and C, and alpha, beta, and gamma, you can construct the entire lattice. The most common kind of 3D lattice is the 3D cubic lattice, where A, B, and C are equal, and alpha, beta, and gamma are also equal, and it's equal to 90 degrees. This brings us to the discussion of Bravais lattice. So as we have discussed, a lattice is a set of points constructed by translating a single point in discrete steps by a set of basis vectors. A Bravais lattice is an infinite array of discrete points with identical environment. In 3D lattices, there are 4 unique Bravais lattices in 3 dimensions. 14 unique Bravais lattices, and they belong to 7 crystal systems. So now we will discuss the 7 crystal systems and the 14 Bravais lattices. The first crystal system is called cubic, which is a simple cube. In that, there are three kinds of Bravais lattices. One is simple cubic, where you have a lattice point at each corner of the cube. The second is called body-centered cubic, or BCC, where you have a lattice point at each corner of the cube and also one at the middle or the body center of the cube. The final is the face-centered cube, or FCC, where you have one lattice point at the corner of each cube and also at the middle of each face. So this is the top face. You have a point at the middle of it. This is a vertical face and you have a point at the middle of it. So that is called a face-centered cube with a lattice point at each corner and at the middle of each face. The second cubic, so in cubic, as you learned, cubic system means A, B, and C are equal and alpha, beta, and gamma are 90 degrees. The next cubic system is tetragonal, where A equal to B, so you can see A and B are equal, but C is different. And alpha, beta, gamma are all 90 degrees. So in the tetragonal cubic system, you can have two kinds of Bravais lattices. Simple tetragonal with a lattice point at the corner, and body-centered tetragonal with a lattice point at the corner and one at the body center. The third crystal system is called orthorhombic. So in orthorhombic, A, B, and C are all different, but alpha, beta, and gamma are all equal and all are 90 degrees. Orthorhombic can be divided into four Bravais lattices: simple, body-centered, face-centered, and base-centered. So base-centered basically means it is a kind of face-center, but it is like there are lesser lattice points compared to face-centered. In base-centered, basically you have one lattice point at each of the corners and one at the middle of the bottom face and the top face. So orthorhombic can be divided into simple, body-centered, base-centered, and face-centered. The next crystal system is called monoclinic, where A, B, and C are all different. Alpha and gamma are equal and equal to 90, but beta is different. So in monoclinic, you can have a simple monoclinic with a lattice point at each corner, or a base-centered monoclinic with lattice point at corners and at the middle of the bottom face and the top face. The final three crystal systems are not subdivided into anything. They are just simple cases. So one is rhombohedral, where A, B, and C are equal and alpha, beta, gamma is 90. And it is only simple, meaning there are lattice points only at the corners. The penultimate one is hexagonal, where A equal to B, but C is different, and alpha equal to beta equal to 90, but gamma is 120. And the final and the least symmetric system is called triclinic, where A, B, and C are different, and alpha, beta, and gamma are also different, and none of them are equal to 90 degrees. So the 7 crystal systems are cubic, tetragonal, orthorhombic, monoclinic, rhombohedral, hexagonal, and triclinic. And the 14 Bravais lattices are shown here. So the crystal systems are defined based on symmetries, which we will learn in the following slides, and not on the geometry of the unit cell. So now we will talk about symmetry. A state in which parts on opposite side of a plane, line, or point display arrangements that are related to one another is called symmetry. So an object or function is symmetrical if it undergoes a certain transformation to look identical to the original. We will first, in this slide, we will just look at the different elements of symmetry, And in the following slides, we will go into the details of each. So one is called mirror or reflection symmetry. So if you imagine that there is a mirror along this dotted line, then one side of the object is a reflection of the other side. That is called mirror symmetry. So in this square, you can have four possible mirrors for the mirror symmetry. Like if you imagine a mirror passing through this dotted line, then one side is a reflection of the other side. Or a mirror passing through this horizontal line. Again, one side of the square is a reflection of the other side. The X-shaped object shown here also has a mirror symmetry. Like if you pass a mirror through this vertical line, one side is a mirror image of the other side. And that is mirror or reflection symmetry. The next symmetry element is called a center of symmetry or inversion symmetry. So basically, this point that I'm showing is the center of symmetry. The concept of center of symmetry is that suppose I start from C. If I pass to the center of symmetry, I should find the same atom C at an equal distance on the opposite side of the center of symmetry. Similarly, if I start from A, I should find the same atom A at equal distance on the opposite side of center of symmetry. So like this, starting from each atom, we should find another similar atom at the opposite side of the center of symmetry. And then we will call it inversion symmetry or center of symmetry. Now, rotational symmetry means that if you rotate the object, it is indistinguishable to before rotation. So this is a star-shaped object. If you rotate this point of the star such that it comes to this point, you can see the final and initial images are indistinguishable. So clearly this has a rotational symmetry. But if you look at this butterfly, you can see that after rotation, these images are not the same. So this has no rotational symmetry. Translational symmetry means that if you translate the object, it appears similar to the original. So suppose you have a crystal with different unit cells placed like this, you can say that they have translational symmetry. Because if you translate the first to the position of the first and second will be indistinguishable from one another. And that is translational symmetry. Glide symmetry is basically a combination of the reflection symmetry and the translation symmetry. So if you look at this triangle and you imagine this line is a mirror, you can see this is the mirror image of this triangle. And after reflection, if you translate it, then this total operation of reflection plus translation is called glide. So the symmetry between the first and between these two triangles is glide symmetry. Now we will look into the details of each of these symmetry elements. So first we will talk about what are symmetry operators. So a spatial transformation can be expressed as an operator that changes the coordinates of every point in the object in the same way. These symmetry operators will not distort the object. It will simply make the object undergo a spatial transformation such that the object is the same before and after the symmetry operation. Just excuse me, I think someone wants to join. I'll just admit them and I'll return. Right, so I'll continue. Yes, so I was talking about symmetry operators. So basically, if you have an object, suppose you have this molecule and you make it undergo a 180-degree rotation along an axis passing through this line. Then what will happen? This 3 atom will come here at the position of 5. 3 and 5 will change positions, and 4 and 6 will change positions. So how can you represent that? By the coordinate system. So if the coordinates of 3 is x, y, z, after this 180-degree rotation, it will become minus x, minus y, and z. So z remains the same because you can see it is still 3 comes from here to here. So it is still in the same plane. So z is unchanged, but the x and y become negative. So this matrix is called a symmetry operator, because if you multiply that with the xyz coordinates, you are getting the final xyz coordinate after 180-degree rotation. So the different symmetry operations can be described in the form of matrices. We will first look at inversion symmetry. So in inversion symmetry, the initial x, y, and z positions all become negative, minus x, minus y, and minus z. So inversion symmetry, as I said, is basically lines are drawn from all points on the object through a point in the center. And if you find, like I'm starting from the thumb to the inversion point, if you travel, suppose x distance in coming here, and you go x distance on the other side of the inversion point, you should also find another thumb. So basically, that is inversion symmetry denoted by I, means the line has to be equidistant from the same points. If so, like the index finger, whatever the distance of the index finger from I, this index finger should also have the same distance from I. Only then you can call it an inversion symmetry. In terms of molecules, if we call this the cis form, because the two CH3s are on the same side, and this is the trans form because the two CH3s are on opposite side. So in the cis form, there is no center of inversion. But in the trans form, the middle of this hexagonal cycle is the center of inversion, because suppose I start from this CH3 to the center of inversion. If I travel the same distance on the opposite side, I will get another CH3. So you can repeat this for all the atoms. If you start from O to the center and you travel the same distance in the opposite direction, you get another O. Or you start from N to the center, the same distance, you get another N. So the coordinates of this CH3 and this CH3 are related, that if one is XYZ, the other will be minus X, minus Y, minus Z. So this matrix is your inversion symmetry operator matrix. Next, if we look at rotation symmetry, the two-fold rotation is basically a rotation around 180 degree. So if you have an axis passing through this center of the circle, suppose the axis is perpendicular to the plane of the slide, and you rotate it 180 degree along that axis, then these 2 points will interchange their positions, but the overall molecule will be same. So that is called a two-fold rotational symmetry. In terms of chemistry, if you look at the water molecule and you imagine an axis of rotation passing through the oxygen, if you rotate the molecule by 180 degree around this axis, H1 and H2 are exchanging their positions, but the initial and final water molecules are not distinguishable. So water is said to have a two-fold rotational symmetry. A three-fold rotational symmetry is, suppose when you have a triangular arrangement like this, and the axis passes through the middle. So if you rotate the points by 120 degrees, the points exchange with each other, and that is called a three-fold rotational symmetry. An example is the pyramidal ammonia molecule. So you know that in ammonia, there is a lone pair on the nitrogen, and so the molecule has a pyramidal structure with 3 hydrogens shown here by H1, H2, and H3. Now you can rotate on 120° on either side, clockwise or anti-clockwise, and your H1 will either change positions with H2 or with H3. Either way, the molecule remains the same, and so ammonia is said to have a 3-fold rotational symmetry. Now, if you have a squared arrangement like this, and the axis passes through the middle, then if you rotate the points by 90 degrees, then the structure remains unchanged. So that is called a 4-fold rotational axis. An example of the 4-fold rotational axis is found in xenon tetrafluoride. So you have xenon and 4 fluorines. If you have the axis passing through the xenon and you rotate the fluorines by 90 degrees around this axis, then you can see F4 comes in place of F1, F1 comes in place of F2, but your overall structure of xenon fluoride remains the same. So this molecule has a 4-fold rotational symmetry. Next is your reflection symmetry. So reflection symmetry exists when the figure can be folded over itself on a line, and the line is called the line of symmetry. So you can imagine it in 2 ways. Firstly, suppose in the square, around each line, you can fold one side of the square onto the other side. Like if you are, imagine it like folding a piece of paper. If you fold along this line, then this side completely merges with the other side, and that is called a line of symmetry. Or you can imagine it like a mirror. So a mirror is passing through this horizontal line, and one side of the square is the perfect reflection of the other side. So in square, if you see, there are 4 such lines of symmetry. Now in rectangle, the 2 sides are of different sizes, and so the number of lines of symmetry reduced to 2. If you have a less symmetric structure like a trapezoid, you will only have 1 line of symmetry or 1 reflection symmetry, or the same for kite. There are other less symmetric structures like a non-isosceles trapezoid where there are no lines of symmetry. So nowhere in this structure can you pass a line such that one side is a reflection of the other side. Now, if you want, so when there is a reflection, you can see the X and Y coordinates remain same, but the line around which you are reflecting, the coordinate of that becomes negative. So this matrix can be called as the reflection symmetry operator matrix. A good rule of hand to remember is that in regular polygons, the number of symmetry axes equals the number of sides in the polygon. So this is a 5-sided polygon, and you will have 5 lines of symmetry passing through the middle of each side. So similarly, for a 10-sided polygon, you will have 10 lines of symmetry. Now, in terms of chemistry, if you look at a tetrahedral molecule like CH2Cl2, this molecule has 2 mirror planes. One plane passes through the plane of the CH2 and bisects the CCl2 bond. And another will pass through the plane of CCl2 and bisect the CH2 bond. These 2 planes of symmetry are possible only because you have like 2H and 2Cl. So there is a possible of reflection of this one. If you have a plane passing, bisecting this CCl2 bond, then reflection of one Cl through the plane onto the other Cl. It is so it is only possible because you have a B2C2 type molecule. If it was 4 different groups, there would be no such reflection symmetry. There are 2 other kinds of symmetry. One is the translation symmetry, which is denoted by T, that generates a pattern in regular identical intervals. So if you start from this star and you translate equal distances in the x direction or equal distances in the z direction or y direction, and you get over here you're getting a two-dimensional lattice. So this star will be said to have translation symmetry. Other examples of translation symmetry, as you can see, this horse is repeated in the x direction, or the chessboard, the black squares are repeated in the x direction, and so are the white squares. Glide symmetry is basically a combination of reflection and translation. So if you imagine a footprint, the reflection of the footprint would be parallel to it, but if you reflect it and then translate it, then it is kind of diagonal to it, and that is called glide symmetry. So now we will just talk about a few points of the different symmetry operators. First is that at first glance, reflection and inversion might seem similar to you, but as you can see from this picture, they are different. So this picture of the rabbit, if you have a mirror along the dotted line, this would be the mirror image. Then you will say that this is reflection. But clearly the rabbit itself does not have reflection symmetry. I'm just showing that if you say that you are carrying out reflection symmetry operator on an object, your object basically is reflected along the dotted line. And if you carry out inversion symmetry operator on an object, basically each point of that object is equidistant to the same point on the opposite side of the object. So if you start from one ear, 2i, and go to the same direction in the opposite side to get the other ear, then you will call this an inversion operator. So if you carry out the inversion operator on this rabbit, you can get a rabbit which is facing the opposite direction, because every point must pass to the inversion point to have the same point on the opposite side. Now, a combination of rotation and inversion is called roto-inversion symmetry. Objects that have roto-inversion symmetry have an element of symmetry called the roto-inversion axis. So here, if you see, you have a point. You are rotating the point. Let's start with one is unity, so that is not important. But if you start from 2, which is the twofold axis of rotation. So if you start from this point, you rotate it 180 degree, it reaches this white point, and then you invert it through a point at the middle of this dotted line. You will get it here. So the relation between the first red point and the second red point is roto-inversion. Similarly, in a threefold roto-inversion axis, you will start here, rotate the point by 120 degree to reach this position, and then invert it through the middle of the dotted line to reach this position. Similarly, you rotate 90 degrees and invert to get a fourfold roto-inversion, and similarly for sixfold. So roto-inversion is a combination of rotation followed by inversion. Now there is a difference between congruent figures and enantiomorphic pairs. So two figures are congruent if they have the same size and shape. So the corresponding angles and sides must be equal. So if you have two triangles, ABC and PQR, AB equal to QR, BC equal to PQ, and AC equal to PR. But simply that is not enough. Even the angles must be equal. So angle A is angle R, angle B is angle Q, and angle P is angle C. Only when these 6 criteria are fulfilled, you can say that one triangle is congruent to the other triangle. So they need to have the same size as well as the same shape. So here, if you see the examples, you can see that these are two congruent figures. Now, these two figures may look different, but they are actually two congruent figures in which you have just rotated one of the figures onto this axis. This is two congruent figures with one being translated, and this is again two congruent figures with one reflected. But ultimately, if you ask about the relationship between the two figures, they are all congruent. The enantiomorphic definition is slightly different. So basically, the two figures are mirrored images of each other, but they are not identical. Then they are known as an enantiomorphic pair. So you know about R and S conformations. So if you have a tetrahedral molecule with four different groups, it is chiral, as you have studied earlier. And if you take the mirror image of that tetrahedral molecule with four different groups, you will get a different configuration. So these two, called plus and minus configurations, that is, they cannot be interconverted without breaking the bonds. So the relationship between these two molecules is that they are mirror images of one another, but they are not identical, because the only way you can interconvert these two molecules is by breaking bonds or changing the configuration. Next, we will talk about simple combination system in which various axes of rotations are combined to generate three-dimensional patterns. So if you combine a two-fold rotation with another two-fold rotation. So basically, if you have a point, a vertical two-fold axis C, if you have this axis and you rotate A 180 degrees around C, it will reach a position B. And you can again rotate it 180 degrees along the direction, this horizontal direction, to reach C. So basically, you are generating a sphere by two-fold rotation axis. I'll explain this again. You start from A. By rotating A through a vertical axis, you reach B. And by rotating B through a horizontal axis, you reach C. So if you repeat this, you will generate a sphere simply by two-fold rotation axis, doing it twice. Similarly, you can combine other axes of rotation. Another element of symmetry, which is a combination element of symmetry, is called an improper rotation. So if you have a tetrahedral molecule and you have this axis, which is bisecting this bond, and you rotate it through 90 degrees, you will get a molecule which looks like this. Then if you, so you have rotated 90 degrees through this axis. Then if you reflect the molecule through a plane that is perpendicular to this axis, you get the original molecule back. So this is a combined symmetry operation where you are first rotating the molecule through 90 degrees and then reflecting it through a plane that is perpendicular to this axis of rotation to get back the same molecule. Then this molecule will be said to have a four-fold improper rotation axis. This is a combination symmetry system, since you have two elements of symmetry, the rotation and the reflection, that is combined. Next, we will quickly go through the point group symmetries. Basically, point groups are used to describe the symmetry of the crystals. The point groups include the elements of rotation, mirror or reflection, center of symmetry or inversion, and rotoinversion. Translation and glide symmetry are not included in the point group symmetry. So for the 7 crystal systems, you can have many different point groups. We are not yet going into the details of this point group. We will do that in the next class. This is just to give you an overview of the different kinds of point groups. There are 32 point groups, and they are divided into the 7 crystal systems. Now that we have gone through the details of symmetry, there are just some miscellaneous points to go through. Firstly, n-fold axis, rotation axis with n5 or n greater than 6 cannot occur in crystals. So if you imagine a, a penta-sided polygon, then and you imagine that it has a 5-fold rotation axis. So you rotate it and it will form. So if you have one unit cell and you keep rotating through the 5-fold axis of rotation, you will get a structure that looks like this. So this cannot form a stable lattice system or crystal, because in some places there is a unfilled space and in some places there is overlap. So unit cell must be in such a way that repeating units of the unit cell fit together perfectly without any unfilled spaces or overlaps. So this 5-sided polygon cannot form a unit cell. Second is the enzyme selectivity. So we talked about the chirality of molecules, and we talked that if we have 4 different groups on carbon forming a tetrahedral like this, then it is a chiral molecule, meaning that this reflection of this will give a molecule with a different configuration. So if you have 2 molecules, there are no symmetry elements between these two. They are 2 completely different configurations. So enzymes are very selective to one particular configuration. There are basically 2 models of enzyme activity. One is called the lock and key model, where the enzyme has certain areas called active sites where the substrates add. And the active site shape is such a way that only, say, the square substrate will add to the squared active site to form the enzyme substrate complex. So the enzyme is very selective in its shape to admit only the specific substrate to which it reacts. And this selectivity is enabled by this chirality. So the chiral molecules at the enzyme active site can only interact with the specific chiral substrate. And once it forms the enzyme substrate complex, it can undergo the catalysis reaction and the products will be released. The other model for the enzyme is called induced fit. So here, the initial shape of the enzyme does not match the substrate shape, but the enzyme can adjust its shape in such a way so as to allow a specific substrate to fit. So the induced fit model allows for a certain flexibility in the enzyme, but ultimately the selectivity remains the same. So while the enzyme adjusts its shape, it can only interact with a specific chiral molecule and not with its mirror image. And again, after forming the enzyme substrate complex, it will undergo the catalysis reaction and form the products. So in mechanism of enzyme, the symmetry is very important in reference to which molecule is actually interacting with the enzyme. Uh, Next, we will talk about the instrumentation of X-ray. So for any X-ray crystallographic experiments, you need an X-ray source. Earlier, this source used to be something called a Crookes tube or a cold cathode tube. So the Crookes tube generated the electrons needed to produce X-rays by ionization of the residual air in the tube. So in Crookes tube, there used to be air inside the tube, and an electric potential used to be applied between the cathode and the anode, and this would lead to ionization of the air, of the molecules in the air. The Crookes tube was unreliable because as the time passed, the residual air would be absorbed by the walls of the tube, reducing the pressure. So eventually, the possibility of formation of electrons by ionization of the molecules in air would reduce because the air would be absorbed by the walls. This increased the voltage across the tube, generating harder X-rays until eventually the tube stopped working. So Crookes tube had a expiration date when eventually there is no more possibility of ionization of the air molecules, And so then the Crookes tube would stop working. Next, the more refined instrument is sealed tube, where the entire X-ray generation system is sealed into one unit, thus eliminating the need for vacuum pumps, motors to spin the target, etc. This system is very compact and easy to maintain. So this is the system that I initially discussed during discussing the production of X-rays, where vacuum is maintained inside the cathode tube and the filament is heated and the electrons formed from the filament are accelerated towards the positively charged anode, and after colliding with the anode, the kinetic energy of the electrons is converted into X-rays. So because the entire system is sealed, it is compact and easy to maintain. The tube is water cooled to dissipate the heat. Most sealed tubes are low powered to avoid overheating the target. So the problem in sealed tubes is that the possibility of overheating is there because, as I discussed earlier, only 1% of the kinetic energy is released as X-ray and the 99% becomes heat. So this heat needs to be dissipated, otherwise there will be overheating. And so to avoid the possibility of overheating, only low powered X-rays can be produced from sealed tubes. After sealed tubes, there was further advancement and rotating anodes were next used. So here the difference is that the anode is spinning. So any heat that is produced is spread out over a larger area. So the problem of overheating is eliminated. Also, because the beam of electron is sweeping a larger area of the anode, it has the advantage of a high intensity of emitted radiation. So here the electron beam was striking only one portion of the anode, and so the intensity was lower. But here the anode is a spinning disk. So the electron is spread out over a large area, and so the intensity is also higher. This system is no longer a single assembly like the sealed tube, but it has two different pumps. So here the new problem comes, which is wear and tear, and maintenance becomes a more serious issue. So here, since it was a single sealed unit, it was easy to maintain and wear and tear was less. But rotating anodes have significantly greater wear and tear. The most newest source of X-ray and which is a source, very large source, is synchrotron. So synchrotrons are large tubular rings under high vacuum in which fundamental particles like electrons and positrons zoom at velocities near the speed of light. What happens is that the positron or electron travels in a straight line until it is forced to turn a corner by powerful magnets at the vertices of the polygons. So you can see there are different polygons forming this synchrotron ring, and at the vertex of each polygon you have a powerful magnet. And since a moving electron has a magnetic field, the electron, when it encounters the magnets at the vertices of the polygons, it is forced to bend. So the electron which was moving in a straight line will now turn to follow this circular path. It costs energy to deflect or change the momentum of the electrons. And that energy is returned to us in the form of intense electromagnetic radiation. So whenever the electron is changing direction, it is losing energy in the form of electromagnetic radiation, and most of this radiation is in the range of X-rays. So the energy that is lost in changing direction can be used as a very powerful X-ray source. If the X-ray source can be increased in power even more if you put insertion devices in the straight stretches of the particle beam. So there is something called a wiggler or undulator, which makes this circular beam move up and down. So the amount of deviation in the path of the electron is significantly increased. So with the increase, so suppose the electron was earlier moving just in a circle like this. Now, whenever it encounters the wiggler or undulator, it will move up and down like this. So when the deviation in the path of the electron is increased, then the amount of energy released is also higher. So these can act as even more powerful X-ray sources than a simple bending magnet. So we have, and since synchrotrons take up a large area, if you want an X-ray source in a laboratory or home, then it is the modern sealed X-ray tube that is used nowadays, which is a variation of the sealed tube that we had studied, but it has three main advantages. That first, the tube is made from ceramic. Next, the beryllium window is visible. And finally, the anode type and focus type are labeled. So it is a more advanced type of the sealed tube. So now that you have the X-ray source, the X-rays can be generated in many different directions. You need something to focus these scattered X-rays. So that is called a collimator. A collimator is a device that narrows a beam of particle or waves. This is to cause the direction of motion to become aligned in a specific direction. In order to get a narrow focused beam of X-rays, the generated scattered X-rays are allowed to pass through closely packed metal plates separated by a small gap. The collimator absorbs all the X-rays except the narrow beam that passes between the gap. So metal plates need to be thick enough that the other X-rays are absorbed, and only those X-rays that are parallel to these gaps can pass through. So from an unfocused scattered beam of X-rays, you can get a very focused X-ray beam. Now that you have a focused X-ray beam, the next part of the instrumentation is called a monochromator. So a monochromator is an optical device that transmits a mechanically selectable narrow band of wavelengths chosen from a wider range of wavelengths available at input. So suppose your input spectrum consists of all these wavelengths shown here. You pass it through a monochromator and only some selected wavelengths, highlighted by this yellow portion here, is the output. So the monochromator partially polarize and unpolarized light so that only a select few wavelengths are applied. So while studying the characteristic and continuous X-rays, you saw that only the characteristic X-ray is of any use. So basically, you need X-rays of a certain wavelength, and the monochromator helps you narrow down the range of the wavelengths. There are two kinds of monochromators. One is called an interference filter, where there is a certain a filter is applied, and the filter allows only wavelength of a certain range of wavelength to pass through, and the other ranges are reflected. So filters exploit the X-ray absorption edge of a particular element. At wavelengths longer than the absorption edge, the absorption is less, and at shorter wavelengths, the absorption is high. So suppose you have nickel metal where the absorption edge lies between 1.54 and 1.39 angstrom. So if you have, so we learned about the K beta and K alpha radiation. So from a copper anode, you will have both K alpha and K beta radiation of wavelength 1.54 and 1.39. So if you use a nickel foil, it can selectively absorb the K beta radiation around 1.39 angstrom, and so only the K alpha radiation will be transmitted through the nickel foil. Here you can see the red line shows the radiation from a copper anode without using filter, and you have substantial amount of both K alpha and K beta. But if you have a nickel filter, then the K beta radiation is absorbed, is reflected, absorbed and reflected selectively. So K beta reduces and K alpha passes through. So the nickel filter is allowing it to monochromate into only K alpha. The major drawback of such a filter is that the background radiation is still high and the transmitted radiation is not very monochromatic. So you can see K beta still persists even though it is reduced. So that is the problem with the filter, that it is not perfectly monochromatic. The other kind of monochromator is called a crystal monochromator. So a crystal monochromator is made up of suitable crystalline material positioned in the direction of the X-ray beam so that the angle of reflecting plane satisfies the Bragg's equation for the required wavelength, and the beam is split up into component wavelengths. So if you have the crystal here, there can be two kinds of crystals, a flat crystal or a curved crystal. So you have a polychromatic X-ray consisting of many different wavelengths, and after reflection, it becomes monochromatic. So according to the Bragg's equation, only those wavelengths are allowed to diffract which satisfy the Bragg's equation. So a polychromatic X-ray becomes monochromatic. And the crystals used in these monochromators are made up of materials like sodium chloride, lithium fluoride, or quartz. So crystal monochromators have the advantage of making the ray more monochromatic. So here it was not very monochromatic because K beta was still persisting. But the advantage of crystal monochromators is that it becomes very much monochromatic. You only get the specific wavelength that satisfies the Bragg's equation. Now that you have generated the X-ray, forced it through a collimator and monochromated it, the final part is the X-ray detector. So X-ray detectors are devices used to measure the flux, spatial distribution, spectrum, and other properties of X-rays. Detectors can be of two types. One is a photographic method. So the X-ray beam falls on a photographic film, and this film is developed and used to calculate the position and intensity of the X-ray beam. So as you know, like in general, when taking a photo, the photo is the photographic film is blackened, and that is the same thing that happens when the X-ray falls on the photographic film, and the blackening of the film is expressed in terms of density unit, given as D equal to log I0 by I. So if I0 is the intensity of the incident X-ray and I is the intensity of the transmitted X-ray, then the total energy that causes the blackening of the photographic film, D, is calculated by log of I0 by I. So you can measure D by an instrument called densitometer, and from that you can find out the intensity of the X-ray. The photographic method is mainly used in diffraction studies since it reveals the entire diffraction pattern on a single film. So you need just one photographic film and you can get your entire diffraction pattern on that. The problem, however, is that it is time consuming and the exposure of the photographic film requires several hours. There are other methods called counter methods, and there are four kinds of counter methods. Firstly is the Geiger-Müller tube counter. So here, this tube called the Geiger tube is filled with an inert gas like argon. The central wire anode shown here is maintained at a positive potential of 800 to 1500 volts. The electron that is formed from the filament is accelerated by the potential gradient and causes ionization of a large number of argon atoms. So this results in the production of an avalanche of electrons that are traveling towards the central anode. And all these electrons that are traveled towards the central anode, basically you are counting the electrons as they are striking your detector. So every time an electron strikes the anode, you get a signal output like this. So basically you are counting the electrons striking your detector, and that is why it's called a counter method. The proportional counter method is very similar to the Geiger tube counter. Only in Geiger tube, argon is used, but in the proportional counter, heavier gas like xenon or krypton is used because it is easily ionized. So like, heavier the molecule, lower is its ionization energy. So it can be ionized more easily. So as it is ionized more easily, it can operate at a lower voltage than the Geiger tube. And so it can count high rates of this electron striking. Since a heavier gas is used, the counter will measure more cases of the electron striking the detector, and so the proportional counter can measure higher density of X-ray. And the next one is a semiconductor detector, where basically the X-ray is falling on a silicon lithium drifted detector. And so when the X-ray falls on the semiconductor, it creates an electron and a hole. Under the influence of the voltage, the electron, which is negatively charged, moves towards positive charge, and the positively charged hole moves towards the negative charge. The voltage generated is a measure of the X-ray intensity falling on the crystal. So basically, if a high intensity X-ray falls on the crystal, then more number of electrons and holes are generated, and so a higher voltage is generated. And you can calculate the voltage by this formula Q by C, where Q is the total charge collected on the electrode and C is the detector capacity. So from the voltage, you can find the X-ray intensity. The final type is called a scintillation detector. In a scintillation detector, there is a large sodium iodide crystal activated with a small amount of thallium. When X-ray is incident upon the crystal, the pulses of visible light are emitted, which can be detected by a photomultiplier tube. And it is useful for measuring X-ray of short wavelengths. So these are the 4 kinds of X-ray detectors by the counter method. And the general principle is that it detects, the general principle of each of the counter methods is that every time the electron is striking the detector, it is giving an output like this. So the problem that was in the imaging method, that it is time consuming, is solved because the counter counts all the pattern instantly. But the problem is that in photographic methods, a single film was enough. But in counter methods, several different counts have to be taken for each of the crystal planes. Now that the X-ray, so we have studied separately the different parts of the instrumentation. So now we will look at the net picture of the X-ray diffractometer. A diffractometer is a measuring instrument for analyzing the structure of a material from a scattering pattern produced when a beam of radiation or particles, in our case X-rays, interacts with it. So typical diffractometer consists of a source of X-ray to choose the wavelength, a collimator to make the beam parallel, a setup of sample holding like the goniometer that we studied in the previous class, and a detector to detect the diffracted signal. An X-ray diffractometer illuminates the sample of material with X-ray of known wavelength. So if you have the sample here, it is illuminated by X-ray of known wavelength after passing through the monochromator. and a strip of X-ray film is mounted in circular position around the sample, like this. The undeviated central beam passes through the hole cut in the film strip, and uh, the undeviated beam will strike here at E. The diffracted beam falls on the film at various positions D1, D2. Basically, the X-ray is getting diffracted by the atoms, and at different angles of diffraction, it will fall at different positions on the X-ray film. And the intensity of the diffraction peak is proportional to the fraction of the material in the mixture. So if you have a large concentration of atoms, then the concentration of that diffracted peak will be higher. And like this, after diffraction, so basically you have your X-ray source passing through the collimator, the monochromator reaches the sample, and from the sample, it reaches the detector, which here is basically a counter. And the concept of the detector is that there is a circular X-ray film around the sample, and after diffraction, the X-ray will strike the X-ray film at different positions, and it can be interpreted into the position of the atoms, and the intensity of the diffraction point can give an idea about the density of the electrons in the atoms. We will quickly go into some of the ways that light interact with matter. So if the light ray, or you can consider X-ray, passes through without deviation, it is called transmission. Reflection is when it reflects back. Refraction is when it passes through the material at a different angle. Diffraction is when it passes through a slit, and then after interacting with, say, the atoms or electrons present here, it will be scattered into different directions. Absorption is when it totally absorbs the beam, and scattering is when it is just scattered in random directions. The difference between diffraction and scattering is that diffraction may be defined as a beam composed of a large number of scattered rays mutually reinforcing each other. So basically, scattering is random, but in diffraction, these scattered rays can constructively interfere with each other and form an intense diffraction pattern. Even scattering can be divided into two types, coherent and incoherent scattering. So in coherent scattering, the scattered wavelets have non-random relative phases in the direction of interest. So basically, even if your scatterers are randomly arranged, the scattered wavelengths are all interfering constructively. In incoherent scattering, the scattered wavelets have random relative phase in the direction of interest. This is incoherent scattering, where your different wavelets from the scatterers have different phases, and there is no relation between the phase of one wavelet with the next. So the path lengths are random. Of all the effects produced by the passage of X-ray through matter, we are primarily interested in the coherent scattering of X-rays. This is because only in coherent scattering there will be constructive interference, and we will get a highly intense diffraction pattern. These are X-rays that we measured in diffraction experiments, as the scattered X-rays carry information about the electron distribution in materials. So we will, as I said, we will focus on the coherent scattering of X-rays. So in coherent scattering, the incoming X-ray, which is an electromagnetic wave, exerts a force on atomic electrons. So X-ray, being an electromagnetic wave, has an electric field as well as a magnetic field. And because of that, it exerts a force on the electrons of the atom. In presence of the electric field of the X-ray, the electron in the atom will begin to oscillate at the same frequency and emit radiations in all directions. This is called coherent scattering, and it is the sum of all the scattering by all the electrons. Electrons are at different positions in space, so coherent scattering from each will have different phase relationships. And at higher scattering angles, the sum of the coherent scattering will be less. So basically, you have an incoming low energy X-ray photon. The scattered photon will possess the same wavelength and energy as that of the X-ray photon. This is because your incoming photon has a certain wavelength and frequency, and it will force the electrons of the atom to vibrate at the same frequency. So whatever electromagnetic radiation is emitted from the electrons of the atom will have the same energy as the incoming X-ray. These scattered X-rays non-destructively combine with each other to form a scattered wave, which represents the scattered photon. Generally, the emitted photon will change in direction by around 2 theta. So if this is your incoming X-ray and this is your emitted X-ray, there will be a difference of angle 2 theta between them. Now we will talk about Miller indices. So the crystal lattice may be regarded as made up of an infinite set of parallel equidistant planes passing through the lattice points. And these planes are known as lattice planes. The orientation of the planes or faces in a crystal can be described in terms of Miller indices. So how are these Miller indices calculated? First, the step 1 is to determine the intercept of the plane along the x, y, and z axis in terms of the lattice constants of the unit cell A, B, and C. So suppose you have a plane like this, and your intercept in the A direction is 3, in the B direction is 2, and in the C direction is 2. So your intercepts are 3, 2, and 2. The step 2 is to take the reciprocal of these numbers. So 1 by 3, 1 by 2, and 1 by 2. The step 3 is to find the least common denominator and multiply each of the numbers by this. So the least common denominator of 3 and 2 is 6. So if you multiply 1 by 3 by 6, you will get 2. And if you multiply 1 by 2 by 6, you will get 3. And in the final step, the result is written in third brackets. So 2, 3, 3 written in third brackets. This is called the Miller indexes of this plane. So once you have the diffraction pattern, you can assign each of the spots by Miller indices. So from the diffraction pattern, you will get 2 pieces of information. The first is that from the geometrical arrangement of these diffraction spots will give you information about the crystal lattice and the symmetry of the crystal. The second is that the intensity of these spots will let you know about the electron density. However, as we discussed in the previous class, we are still lacking the phase information. So there is a loss in the phase information. Next, each of the spots will be indexed by the Miller indices, and the intensity of the spot can be assigned. So the indexing procedure determines the unit cell dimensions. From the Miller index, you can calculate the unit cell dimensions and the lattice type. So basically, this is a diffraction pattern, and this is showing an enlarged portion of that pattern. During indexing, you have to find each spot and you have to name them with integer numbers of the Miller index. And from that, you can find the crystal geometry. And you can then integrate the intensity to find the distribution of electrons. Now that we have talked about the crystal and diffraction, you need to understand the real space and reciprocal space. So basically, every crystal has associated with it a crystal lattice and a reciprocal lattice. So you have the original crystal structure, and the crystal structure has a crystal lattice and a unit cell. Now, if you get a diffraction pattern from the crystal structure, the diffraction pattern is a map of the reciprocal lattice of the crystal. So whatever from the diffraction pattern, what you are reconstructing is called a reciprocal lattice or a reciprocal space. So the immediate result of the X-ray diffraction experiment is a list of X-ray reflections HKL and their intensity I. So this is the result of a diffraction experiment. You have many different spots with HKL, Miller index values, and intensity. We can arrange the reflections on a 3D grid, and based on the smallest repeat unit of this reciprocal lattice, which is called the reciprocal unit cell, we can find out the length of the original crystal lattice. So there is an inverse relationship between the diffracted intensity and the real space. So if you look at the comparison between real space and reciprocal space, real space is defined by the real unit cell, which has the lattice parameters A, B, C, and alpha, beta, gamma. It also has a certain electron density and atomic coordinates. And corresponding to the atoms, it has bond lengths, bond angles, and crystal faces. The reciprocal space, on the other hand, is derived from the diffraction pattern, and it has the integrated intensities of each of the spots defined by HKL, and it has the structure factor and phase, which we will study in detail later. So finally is the X-ray diffraction data processing. We are not going to go into details of that right now. I'll just talk about that in the very short. So these two images show two successive detected images with a crystal rotation of 1 degree per image. So basically, this is from a certain position of the crystal. And then if you rotate the goniometer head on which the crystal has been mounted by 1 degree, this is that after 1 degree rotation, this is the diffraction image. So from data collection, we can find a number of oscillation images where the crystal has been oscillated by several degrees. And in data processing, these set of oscillation images is converted into a file that contains the intensity I and sigma of the symmetrically unique HKL reflections that were measured. So in data processing, there are 4 main steps. One is you collect the initial images like this. You evaluate the crystal and index each of the spots by HKL. Then you collect the full set of oscillation images. So oscillating the crystal from all different angles on the goniometer head, all the oscillation images are collected. Then the reflection intensities are measured, which are a function of the HKL to get the distribution of the electrons. And then finally, scaling, merging, and averaging of the reflection intensity data is done to get a picture of the entire crystal from different angles. So this concludes our discussion on the instrumentation of X-ray crystallography and symmetry. So now we will go through some sample questions. The first question is that which metal is generally used as a target anode to study protein crystallography? I'll give you some time to go through it, and then I'll discuss the answer.
Copper.
Yes, that is correct. So the correct answer is A, copper. And so I'll discuss it now. So why copper? So since the target has to be metallic, so that it conducts electrons, it has to have a reasonably high melting point, because you are having thermionic emission of electrons. So it has to be heated substantially, and so the metal has to have a significantly high melting point. So this limits your choice of anode to chromium, iron, cobalt, copper, and molybdenum, and a few other less commonly used materials. But copper anodes are by far the most commonly used because copper gives the shortest wavelength above 1 angstrom. So if you look at the wavelengths produced by molybdenum and silver, they are too short for most of the diffraction work. If you go back one second, if you go back to the wavelength range that you see here, then the wavelengths produced by copper fall within here, but by molybdenum, silver, and some other metals, you get even shorter wavelengths. So those wavelengths will pass through the gaps in the lattice and it will not be able to detect the atoms. So that is why copper is ideal, because the copper wavelengths are not that long that it will pass completely outside the compound, and they are also not that short that they will miss the atom. So that is why copper is most commonly used as your target anode to study protein crystallography. The next question is that what is the wavelength of the K alpha radiation that is commonly used for the copper anode?
Option D, 1.54 angstrom.
Yeah. So the correct option is answer D. So as you can see, in all the metals that are allowed to be part of the anode, the wavelength of copper is 1.54 angstrom. So this is actually the wavelength of the K alpha radiation, which is when there is a vacancy in the K shell and an electron jumps from the L shell to the K shell. So that is the K alpha radiation, and that is what is most commonly used in X-ray crystallography. And the particular wavelength, as you said correctly, is 1.54 angstrom. There is also K beta, where the electron jumps from M shell to K shell, but that is not used much. So the next question is that which small molecule anode is used for small molecule crystallography?
Option A, molybdenum.
Yeah. So once more, if you compare the wavelengths, copper is used for the normal crystallography and silver is too small, so it will completely pass through the gaps in the lattice. But molybdenum with 0.71 angstrom, if you compare, like this is the wavelength of molybdenum, K alpha, K beta. If you compare that with copper, molybdenum has much smaller wavelength. And so the small wavelength helps in detecting in small molecule crystallography. The next is that if a photon is released from an electron transition from M shell to L shell, what is the transition known as?
K alpha.
The answer is actually L alpha. So if you look at the nomenclature of the transitions, so from the M shell coming to the L shell is known as L alpha. K alpha is actually from L to K. So if you just remember this chart, you can remember the different nomenclatures. And as we had previously discussed, even in M, you can have many different subshells. So even for the L alpha transition, it can have different energies like L alpha 1, L alpha 2, and so on. So the next is that if a photon is released from an electron transition from the M shell to the K shell, what is that transition known as?
This will be K alpha.
It's K beta actually, because it's M to K. So L to K is K alpha, M to K is K beta. So basically the way this is named is that the first letter comes from the shell that it is goes to finally. So if your transition is to the K shell, it begins with K. And if it is from L, that is the shell that is directly after K, then it is alpha. If it is from M, that is K, L, then M, then it is beta. If it came from N, suppose, then it would be K gamma. So the first letter is always to the final shell that is going to. And if it comes from the one immediately after, it is alpha. Next one, it is beta. Next one, it is gamma, and so on. So here your correct answer is actually K beta. The next, so here you can see that. The next question is that what is the building block of a crystal defined as?
Unit shell.
Yeah, the correct answer is unit cell. So as you can see from crystal lattice, the building block is unit cell. And if you are asked that what are the unit cell parameters, then for a 3D lattice, it is A, B, C, the 3 sides, and alpha, beta, gamma, the 3 angles. The next question is that what type of lattice consists of 2 distance and 1 angle parameter?
2D lattice, 2-dimensional.
Yep, that is correct. The answer is B. So the first example here shows a linear or 1D lattice where you have only one parameter, the distance between 2 lattice points. The others are all examples of 2D lattices. So you have 2 distances and 1 angle. So in square, you will have 2 equal distance AB and an angle. In rectangle, A and B will be different, and you have the angle, which is again 90 degrees, same as square. In a parallelogram, again, A and B are not equal, and the angle is not 90. Then you can have hexagonal, where A and B are equal, and the angle is 120. So it forms a hexagon like this. And finally, you have a centered rectangular, where you have a rectangle and a spot at the middle of the rectangle. So this is like a body-centered cubic lattice. So similar to rectangle, your A and B are not equal, but your angle is 90. The next question is that what is unit cell shape of a 2D square lattice?
Option B.
Yeah, so we just studied that in the previous question. So your 2D square lattice consists of A and B being equal and alpha, the angle between A and B, being 90 degrees. The next question is that how many lattice parameters are present in the 3D lattice?
Option C.
Yeah. Coming back to the 3D lattice, there are 3 distance A, B, and C along X, Y, and Z directions, and alpha, beta, and gamma, which are the distance angles between these distances. Then, so this is a question that consider a plane ABC. It has intercepts of 2 units along the x-axis, 3 units along the y-axis, and 2 units along the z-axis. What will be the Miller indices of this plane?
Option A.
Yes, so the way you are calculating that is the step 1 is to determine the intercept of the plane along x, y, and z. So that is mentioned in the question as 2, 3, and 2. The next step is to get the reciprocal of this number. So 1 by 2, 1 by 3, and 1 by 2. Next is to find the least common denominator. So for 3 and 2, the least common denominator is 6. You multiply 1 by 2 by 6, you get 3. 1 by 3 by 6, you get 2. And again, 1 by 2 by 6, you get 3. And finally, you write the 3 numbers in brackets, 3, 2, 3, to get the correct answer as option A. The next question is that according to Auguste Bravais, in a 3D system, how many possible lattices can form?
14.
Yes. So as we have discussed, there are 14 Bravais lattices and 7 crystals. So if the question was that how many crystal systems are there, that is 7, which is cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. And in the 7 crystal systems, you can have 14 possible Bravais lattices. Next is that what is the adequate number of lattice points in a body-centered crystal system?
2.
Yeah, so that is the how that is calculated is basically if you look at a simple cubic system, each of the lattice point is actually 1/8 of a total atom. So you have 8 lattice points and you have 1/8 of an atom at each of the 8 points. So 1/8 into 8 is 1. In a body-centered system, it is similar to cubic, but you have an extra lattice point at the middle. So it is 1/8 into 8 for the ones at the side. So you get 1 from that and 1 in the center. So that will give you 2. In face centered, again, it is the simple cubic, but you have a half of a lattice point at each of the faces. So there are 6 faces and you have half lattice point at each face. So that is 6 into half. So 3 lattice points. And from the simple cubic at the sides, you have 1. So 3 plus 1 in a face-centered cubic cell, you will have 4 lattice points. So if your question was face-centered, your answer would have been 4. But here your answer is B. And the final question for today is that the 4-fold rotation operation moves the object by how much degrees?
90 degree.
Yeah. So your answer is B. So the how this is calculated is that basically if you have 360 by the 90 degrees, you get 4-fold. So if you are mentioned 4-fold, you can divide 360 by 4 and you will get the total degree by which it is turned, which is 90 degrees. So here in the cube, you can see it has 4-fold symmetry because if you turn it around this axis passing through the middle, by 90 degrees, then it is unchanged. Similarly, if you were asked that 6-fold, you divide 360 by 6 and you will get 60 degrees. So whatever fold, n-fold is given in your question, you can just divide 360 degree by n and you will get that how much degrees it is turned to remain unchanged. So that is all the questions I have for today. If you guys have any doubts, you can clear them. Any problems with the assignment questions or any doubts, you can clear them now.
Hello, ma'am. Good evening.
Yes, yes.
Ma'am, actually, I joined a little late because of the network issues. Ma'am, can you please tell me about the symmetries, like a little bit brief, if it is
Okay,
possible?
yeah, sure.
Can
Wait, I'll
elaborate?
just come back. Wait.
Okay.
So will I talk about each of the elements of symmetry?
No, ma'am. Like from inversion, I was able to listen properly. Ma'am, before inversion, yeah,
So,
symmetry operators. Yeah, ma'am.
okay.
Till this, I was not able to connect, ma'am.
Okay, so before this, for symmetry, before this, I had only 2 slides. So in, I'll just discuss those. And so this is, in this slide, I had basically talked like the symmetry elements that are elaborated later. That is only given in short in this slide. So I think this you have understood, right? Each of the symmetry elements.
Yes, ma'am. Yes.
So I'll just go to the next slide. So basically what I was talking about here is that how the symmetry operator can be represented by a matrix. So have you learned matrix multiplication?
Yes, ma'am. Yes.
Yeah. So if you multiply this matrix with x, y, z, you will get minus x, minus y, and z. So suppose you have this molecule. if you make this molecule undergo 180-degree rotation around an axis passing through this line, then 3 and 5 will exchange positions, as you can see, and 4 and 6 will exchange positions. So if you look at the XYZ coordinates of 3, if initially the XYZ coordinates was just XYZ, after this 180-degree rotation, in the new position of 3, the coordinates are -x, -y, and z. Z is same because this Z axis you are rotating around the Z axis, but X and Y become minus. So this matrix is representative of a 180-degree rotation around the Z axis, because if you multiply by this matrix, you can get the final position of the object. So like this, each of the symmetry operators can be represented by a three-dimensional matrix, which if you multiply the initial position of the object, you multiply with the matrix, you will get the final position of the object. So this was what I was discussing.
Okay, ma'am. Thank you. Thank you so much.
Okay, sure. And other than symmetry, uh, the rest was just introduction part. So like the production of X-rays from cathode ray tubes and all. So did you have any problems in those parts?
No, ma'am. Actually, I have visited to your lectures, recorded lectures. So,
Okay, great. So any other doubts if anyone has?
ma'am, can you please show up once again the congruent? You mentioned
One sec.
something
Yeah.
like congruent.
Yes. So this slide you're talking about?
Yes, ma'am. Yes. So, can you please little bit elaborate it?
Okay. So if you have two figures and the sides of the figures are equal. So suppose I'm labeling this A, B, C, and D. Then the length of A is same in both, length of B is same in both. Like that, all the sides are equal and all the angles are also equal. Then you will call it a congruent figure. If you are asked the relationship between these two figures, you can say that they are mirror image. But if you are asked if they are congruent or enantiomorphic, the answer is that even after reflection, the figure is congruent because this side equals this side. This side equals this side. Similarly for the other two sides. But in enantiomorphic figures, um, like you have learned about chiralities. So if you have a carbon with 4 different groups and you take a mirror image of that molecule, you will get a molecule with a different conformation configuration. So in congruent images, the property is that they can be superimposed. Like these two images, you can just move this to this side and then move it up and it will superimpose. Even in this reflected, if you reflect it back by 180-degree, it will superimpose on this image. But in enantiomorphic, you cannot superimpose them. The only way that one can be interconverted into the other is by breaking the sigma bonds. So that is the difference between congruent and enantiomorphic.
Okay, I got it. Thank you.
Okay, sure. I'll just wait a couple more minutes if anyone has any other doubts. Okay, I think there are no more questions, so I'll just stop the recording.